Okay, and I won't linger as long as we are done. Okay, so here now we come to 5.3, unbiased estimators. Unbiasedness, as I explained a little bit before. So now use this example 5312.
Excuse me, Professor.
Yes.
I don't see your desktop. Did you
Oh,
share it
okay,
again?
okay. I forgot to share. 1 second.
Okay.
Okay. All right. Okay. Can you see it now?
It's coming.
Perfect.
Yep, we're good.
Okay. Sorry about that. Okay. Okay. So now we previously we talked about the unbiased estimator, and so in this case we shall see an example to see why we say that. And here, the moment let's verify the moment estimator of P. P is a P hat and Bernoulli from the example we studied previously. Then so you can see that P hat equals to the actually is the average and average of the x, and we denote the sum to be y, sum of x to be y. So the expected value of P hat equals the expected value of y over n, and you take out the n because n is a constant. We will get that because expected value of y is NP. Why? Because Bernoulli is a special case of binomial. When binomial has n equal to 1. And when you have put the n Bernoulli together, you make it a binomial. So that's why binomial, that's why we look at the sum of x for y. And that's why the expected value of y is the n times p. Okay. And np over 1 is p. So so that means expected value of p hat equal to the population parameter p, and that means the difference of them is 0, no bias. So unbiased estimator. Now here many people don't know why S square is an unbiased estimator. Why n minus 1 in the denominator? That makes things confusing. But because of this reason, if you don't subtract 1 in the denominator, it is not an unbiased estimator. And this we can prove by taking the expected value of S square. And so S square is that, and you take the expected value of that, and is the expected value of this thing, and develop it. Well, rearrange it this way and develop it. You will be able to get this first item is variance. The second item is the second item here is n, and let me see. The second item here is variance divided by, the second item here is a sample variance. I mean the sample variance or sampling distribution of the sample mean, right? Yeah. So with that becomes 0. Yeah. So again, let me see. With that you have the n minus 1 times sigma square. here in the bracket, but then divided by n-1, so you get sigma squared. In other words, that result shows that the differences between the expected value of S squared and sigma squared is zero. So that's an unbiased estimator. However, almost done with this one. However, unbiased estimator doesn't make it the best. So we need another criteria, which is minimum variance. So that brings us to the what? This definition of mean square error as another criteria for determining, for filtering out the useless unbiased estimators. You may have a bunch of unbiased estimator for the parameter, but only one has the minimum square of square error. If you have a lot of square of error, that means it's not accurate, is not precise. So define the mean square errors. That's just the average of the squares of the errors from the estimator, between the estimator and the parameter. Okay, so you can calculate this way. We skip the details, and then what? Then if we let the B is that, as we've seen the same previously, and we will see, but we also see that MSE is that. So rearrange it, then you can see MSE of the theta hat equal to variance plus B square. Okay, B square. But we know that expected value of that is that equal to 0. Okay, so that is MSE. Okay, so when unbiased estimator make it MSE equal to variance, because variance is actually average sum of squares. Okay, mean average sum of squares of errors. Okay. If you look at this example, you will see that expected value of theta 1 hat equal to expected value of x bar. Based on this example, is not a special distribution. It's just three randomly a toy example. Okay, so n equal to 3, and the expected value of the x bar equal to what? Equal to 3. Yeah, equal to the 3 mu, because let me see, x expected, yeah, because theta here we see that theta 1 hat equal to x bar, so the expected value of theta 1 equal to expected value of x bar. But you can rewrite it. Let me see. But x bar, you have 3, and okay, yeah, the way it arranged it is kind of weird, but that's fine, because yeah, expected value. What that means, expected value of x equal to mu. Okay, and that 1/3 times 3 is kind of confusing. Okay, don't worry about that. And then theta 2 with another estimator. Okay, expected value of it is equal to the expected value of you put the expected value before each random variable x1, 2, 3. Then you will have 2, and each expected value of x will be equal to the center, because mu. because they follow the same. They are from the population that has that follow mu as their population mean. Okay, then you get so they both are. The point is they both are unbiased estimator. But then you calculate this variance, you will see that one is sigma square over 3, and the other one is that. And because of the first one is less than the second one, then X bar is better than the second one. We always want not just unbiasedness, we need the minimum variance, minimum mean square of error. Okay, so we call it mean. The unbiased estimator say that minimize the mean square error is called MVUE. Okay, of the theta. Okay, we'll skip the sufficiency. It's very long. Okay, we will go to, for the sake of time, 5.4. 5.4 is confidence interval using pivotal method. Okay, look, in statistics, we want to construct a confidence interval because, you know, giving mu as a target and X bar as a bullet, in an analogy of firing a rifle shot with a rifle bullet, the result to hit the target, the bullseye, the result will be hit or miss, because the rifle bullet hit the thing with the point, not the range. And so even if it is missed by the width of a hair, it's still a miss. So in statistics, we can do things like that to estimate the point population parameters. So we construct an interval. Is similar to the sense of firing a shotgun bullet and hit the target with a range. And the range is the upper bound and lower bound you see here. Upper bound mu and lower bound alpha. But of course, even with the bound like that, we can still miss the target. But nobody, given that nobody really know where the target is, so we can only give it an error, and the measure of error is alpha. And alpha usually go from 0.1 to 0.01 to 0.1, 1% to 10%. Okay, so our goal is to construct an interval that will 90% of the time, I mean, suppose alpha is 10%, then to construct an interval that 90% of the time will capture the target. And although theoretically speaking, nobody really know what the target is, where the target really is, and by this kind of rationale, we can scientifically state with confidence that 90% confidence, or 1 minus alpha times 100% confidence that the interval will include the target. Yeah. Okay. This is a background, and so how do you get that? For example, let me give you the example. We know that this is a standard G transform. We call it standardizing the formula standardize any normal distribution members to to the standard normal distribution member, which is a unique member in the normal distribution family. Now that X bar is qualified to central leaving theorem to follow a normal distribution with mean mu, which is mu X bar, but mu X bar equal to mu. And then divided by sigma X bar, I mean X bar in the subscript, but sigma X bar is sigma over square root, and we saw it previously. So this kind of and X bar is a random variable. So through this kind of standardizing, we can identify X bar with Z in this way, having such a relationship. Okay, but you can see that let me see, sigma. I think sigma. Okay. Well, we don't usually write it that way. Like here, I highlighted just the left hand side. Okay, because we don't know sigma. Okay. Now, so, and what's the upper bound and lower bound? You know, based on the normal distribution, a confidence interval. 90% confidence interval has 5% on the upper tail and lower tail, and so on and so forth. So that means the right tail is alpha over 2, the left tail is alpha over 2, and one, because it's symmetric about the center of the distribution, so it's positive and negative. All right. So that's upper bound and lower bound. So given that this formula here, upper bound and lower bound, okay, and now z is a parameter. You plug in that z a parameter, plug in here, and z is that, okay, and equal to 1 minus alpha. Alpha is 0.05 in this case. So you have these numbers plug in, and this z alpha over 2 is z with a subscript 0.025. So if you draw a normal distribution, you have 0.025 to the right of that z alpha over 2, when alpha is 0.05. That's so it's z 0.025. It has 0.975 to the left, and you either look up that value in the table, normal distribution table, or Excel, you will get 1.96. All right, so with that, you then what? You plug in z equal to x bar minus mu over sigma over square root n. Right here, you plug that in. Rearranging it, you will get that. And guess what? That's the pivotal method, because you successfully constructed the upper bound and lower bound to capture mu. Okay, and we can say, so looking at this, you should know that we are 95%, or with the probability of, we call it 95% confident that that this mu, which nobody know what it is, shall be enclosed, shall be captured by that range, shall be hit by that range of my statistical rifle bullet. You know my analogy. And now statistical shotgun bullet. Okay, so that hit the target with the range, and that's the range. Okay, so I think that's good to explain that matter. We run a little bit longer today. I don't want to go longer than that. So I'll leave the homework to you, and you are free to ask me when you get there and have questions, I'll be glad to help you. All right, Paul, any questions?
I think this is, this is an area that has always kind of confused me, especially around the moments and things like that, the terminology and trying to get it clear in my own head between
Yeah.
whether we're talking about a population or whether we're talking about a sample.
Right,
So I think
right.
I just need to go back and go through the material again, that you've reviewed tonight. And then if I have any questions, I'll email you.
Okay, okay, definitely. Yeah, it takes a few times to sink in. It's not that straightforward.
Yeah,
It's quite abstract. But
it
remember,
is.
keep this big picture in view. My analogy in view, which is what? Target and bullet. Okay,
Yeah, yeah,
everything like mean standard deviation in the population is the target.
yeah,
Everything in the sample is a bullet, and
yeah,
well, this chapter is to the job of this chapter is to show us how we find the best bullet which can
right.
hit the target.
Yeah, yeah. No, you're right. And the thing that confused me and has for a long time when it comes to this is that, I've learned statistics from the sample point of view, so we're always trying
Oh,
to take a sample and we're calculating the mean or standard deviation or some sort of parameter. And
mhm.
now this chapter kind of flips it, I
Yeah,
think. Yeah, and it's kind of like, okay, now we're looking at the population. We don't really know the population mean
right,
yet. What we've learned is that we're trying to estimate the population mean using a sample, but now, we're talking about the population mean, which is unknown. So
right,
how do we estimate that? And
right,
that's
right, right, right,
it's
right.
just kind of a reversal of, I think,
Hmm.
how we've learned things in the past. So
Right.
that's what's confusing. And I've got to review it.
Yeah, exactly. And so this chapter is to tell you how statisticians come up with different
Yeah.
bullets,
Right.
of the sample. One bullet is a maximum likelihood estimator as a bullet.
Right.
One is what a matter moment, and then we study whether these bullets will hit the target or not.
Right.
They need to be unbiased. Okay, if not biased, if it is biased, then you will hit the target very well. And then and also, okay, given it's unbiased, we still not sure if they will hit the target.
Right.
So we create an interval that increase the probability, our confidence to 90% to 99%, depending on R, so that will help us to hit capture the target.
Right. Right.
Target is all that we want. Okay. So
Okay. That's
yeah,
great.
if you have that big picture, my analogy in view, then this will be greatly simplified. The
Okay.
detail maybe, yeah, the details are important in calculating in working out your assignment, but the concept is most important in the
Yeah.
understanding of it. Okay.
Okay. Got
All
it.
right. Good. I'll let you have dinner.
You didn't hear any pounding in the background, did you?
I didn't, but I just am thinking this is your dinner time.
It is.
Okay. All right.
All
Okay.
right.
I'm glad
Thanks
to
very much.
be happy tonight. Okay. Have a good weekend. Okay.
Okay. Thank you. You too. Goodbye.